So two important links. The first link, that's the Galaxy instance we are going to use. Part of the reason so Greg Van Kooster and I organized this workshop. Greg Van Kooster is not in town today, but he will be here in the next workshop. Is that Greg actually created an instance dedicated to Penn State. It has a different URL. It has most of the functionality of that system, and the difference there is that there are much shorter job queues. So if you start your jobs, they'll compete faster. And so just to popularize that, and in general to make people aware of what can be done, we organized this workshop. So this is a global. This is one of the three global instances. It's I guess targeted towards North America. I mean, you can access it from anywhere. It runs out of multiple locations, but its primary servers are in Texas, University of Texas supercomputing center called the Texas Advanced Computing Center. That's why we have capacity to serve the world. There are two more instances, one in Europe, it's usegalaxy.eu. There's also Australian instances, is usegalaxy.org.au. There are also French, Belgian, soon Spanish, many other, Estonian, many other instances. But these three ones, American, European, and Australian, have the highest capacity. And this link, it's just training at galaxyproject.org. This is a great resource for all kinds of training materials. So you can see it has different categories. There are lots of tutorials, and I don't know anything about proteomics or metabolomics or imaging. I know some things about genomics. But you can see that in its core, Galaxy has nothing specific to biology. It's just a framework which wraps tools and provides a really large compute to run them. So this is it's a key point here is that not only we provide the tools, we provide the compute. This compute it's using a cloud, but not commercial cloud. It's using cloud, which is in US is funded by NSF. It's so-called Access project, which used to be called Exceed. It's essentially a link of multiple supercomputing centers, and so we use it for providing this portal-like capacity for thousands of people. But if you need a compute, for example, if you do something, I don't know, you're assembling some crazy plant genome, and you need some insane amount of compute. You don't have to run to, VP for research here and ask to buy servers. You don't have to pay Amazon or Google or Microsoft. You can just go to, you can just Google for Exceed or Access-CI. If you email me, I can email you these links. And you write a small application, and they give you compute. How much you ask? I don't know, 20 million service units or something like that. So not all clouds are private. That's the message here. Okay, so what I wanted you to do, so this is Galaxy, we'll start from here. I'm using the public instance. The way I got here is I clicked on that login link. So I already, pardon my account name, but So, so I can just go ahead and log in. And you should see something like this, which, if you've never seen it before, looks like some website with some text. So now you can go back, we'll just open a different tab, go back to your email and click that link that I sent you. What this does is there are, some number of us here, I don't know, 15, 20 people. But you're competing against a few hundred or 1,000 who are using it right now. And so for running training workshops like this, we have a dedicated queue. So all the jobs that we will be running here, they will not be large jobs, they will be relatively small jobs, small analyses, obviously, because we want to finish today. But they will go to a special cluster, you might say, where there is no wait. So that's the whole reason for this link clicking. I mean, you don't have to do it. You can just use it the way it is. You might get stuck behind somebody, so it will take longer. Any questions so far? Did link work for everybody? Is life good? Okay. Yes. I understand that if link works, then life still might not be good and vice versa. But yes, those are not really correlated things. Okay. So today we're actually going to run a very simple, very quick, well, it's not actually, I don't know if it's a little bit quick. We're going to run an analysis which has no biological data at all. We're just going to manipulate some data sets, and idea of this little analysis that we can do today is to show you how this, for example, how the history system works, how the tools work, and in general, it's a good exercise for manipulating, in this case, tab delimited data. So most of the genome analysis, as you know, it's just it's changing one file format into another. For example, even if you're doing genome assembly, you can argue that you sequence, you generate files of one type, then you assemble these reads. Well, it's essentially a file of a different type. And then you annotate that genome, that's a file of a different type. And then you always do this file manipulation. Well, in case of genome assembly, at least you get a sequence. So that's sort of a one singular thing, if you're lucky, if your coverage is high enough. But in other cases, like for example, there's a lot of Galaxy used for gene expression analysis. When you do gene expression analysis, you get tables, that gene, that expression level, and in that condition, and so on and so forth. So this is all kind of a tabular data. So these are the tools. Galaxy has quite a few. So we have something like on the order of 4,000 different tools. Tools are individual things that you run. For example, if you've if you ever dealt with sequencing data, you get the reads from here, from hardcore facility, and you map them against some genome using BWA and Bowtie. So Bowtie is a tool here. Or if you're doing gene expression analysis and you're running DESeq2, DESeq2 is a tool. That's what I mean by tool. So any kind of a command line utilities you can run. And some of them are very generic. So today we're going to use a lot of text manipulation, this data munging stuff. But some, of course, are more specific for sequencing data, or for computational chemistry, or for image analysis, and so forth. And actually, one of the interesting problems that we're having is that 10 years ago, this was not that messy. But today, the problem that we're having is that we have too many tools. And so so there's this search bar, and there are various ways in which you can organize this. It's still a work in progress, because it's, you can put a tool in a category depending how you think about it. So it's not really one-to-one mapping, unfortunately. But anyway, so what I want you to do, any problems? Anybody's having problems? Problems with login? Okay. So I don't know the level, sort of a skill level. Well, actually, before I jump here, let me briefly talk about this. So I don't know your skill level. So for some of you, it might be very boring. For some of you, it may be too far ahead. So today is introductory thing. So we're going to take one data set, and we're going to do different things to this, and you will find this useful for any kind of data you're in. Even if some of you are TAs and you're dealing with tables with your students, you can apply the same idea here. So next week, we are going to get some COVID data. I mentioned COVID is a good thing because it has small genome, but it's applicable to any sequencing data set. In this particular case, this will be Illumina data. But I pointed out that if you have Oxford Nanopore or PegBio, then we can just ask questions. We'll see. So that would be a little bit more complex because in this case we're going to analyze lots of data sets. So today we're just going to practice, look at it, how it works, and so on. But next Monday we are going to have a taste of reality because in reality you usually don't have one sample. If you're doing a good experiment, you have multiple replicates. For example, in case of COVID, you have multiple time points, and so on. So it's rarely that your data has just one sample. If you're doing gene expression analysis, for example, you have multiple individuals, multiple conditions, and so on. So it's multi-dimensional. And so next Monday we're going to deal with more of a real data set, which has, I don't remember, maybe 50 samples or something like that. And we also, well, that's going to be in 3 weeks after that. We're also going to deal with how to organize complex data sets. Again, data sets where you have, again, multiple samples, how to deal with them, how to assemble them into one entity, separate them into different entities, parallelize analysis that you're doing in them, and so on. We're going to talk more about tools. So on December 5th, we're probably going to we'll talk about, I would ask you to tell me which analysis you would like to do, but we're going to talk about various things like genome assembly, gene expression, variant analysis, the protein and nucleic acid interactions kind of things. On December 12th, we're going to talk about workflows. So what workflow is when you take multiple tools and assemble them into a chain that you can then automatically execute. And on December 19th, this is for if you want to use Galaxy programmatically. Because today we're going to use it through graphical user interface, but for many people who do data analysis for a living, graphical user interface is not necessarily a good thing. So here we're going to talk about how to add tools. If you, for example, wrote a tool and you want it to be used by the community, how you plug it in, and how you use Galaxy using application programming interface or programmatically. So, for example, you're some small country or large country that wants to establish monkeypox monitoring system, and you collect data, and you just need to analyze it, say, on a daily basis, 100,000 samples today, and so on. So you can just automatically submit these samples and get your results. That's what we're going to talk about on December 19th. Anything missing? Any suggestions? Either raise your hand or email me. You now know my email, I suppose. Any questions so far? Okay. So let's go to the training page and let's go to Introduction to Analyses. There's lots of them. So there's Galaxy 101, which is the first time probably did 12 years ago. Of course, it's all updated. But I thought that we're going to do something slightly more advanced than usual. And specifically, we're going to do this data manipulation Olympics. It's a good exercise to go through. So, in a browser, you have multiple tabs. So make sure that one of your tabs is Galaxy. And the other tab is this training. To get here, you go to training.galaxyproject.org and go to Introduction and go to Olympics. If you want to go at your own pace, go ahead. This is a kind of interactive tutorial. But if you want to listen to me, that's good too. So this is just a website. So we have tools here. There's some central pane, and this is also some gray area in this interface. So they all have names. This is our tool pane. This is tool interface, you'll see it here. And this is history. So history is an important, this is where all your data goes, all results of your analysis go. It's a kind of a workplace for a given analysis. You can have multiple histories, of course. And you can also share them. So for example, you do something and then you work with somebody, I don't know, in San Diego, and you send them a link, and they bring it in, and they start building on what you gave them. But before I explain to you history features, maybe let's put something there. So the first thing is to get some data, and let's upload some data. So this is URL, it's a link to a file. And what I'm going to do is I'm just going to copy it into clipboard, go to Galaxy itself, and click on this Upload Data button. And there are many ways in which you can get data. You can upload files from your computer, obviously. You can get remote files. It's an interesting thing I'm going to just mention. So there are lots of data sets here. These are large public data sets. For example, if you're interested in all vertebrate genomes, actually general animal genomes, this GenomeArk. This is a it's a repository for VGP. VGP is a vertebrate genome project. The goal of vertebrate genome project is obviously to sequence all vertebrates, but they're sequencing insects as well, and there are plant genomes there as well. 1,000 genomes data sets. This is some public data from TCGA, because TCGA, of course, is not public. You need to have GBGAP access to it, but there are some data sets which you can use and so on. But that's not what we're doing right now. Right now, we're going to click on Paste, this button here, Paste and Fetch Data. And you just, you just paste your URL in here, and you click Start. I can close that thing. And so here's you have your first data set in the history. It's right now what's happening. It's getting transferred from whatever Zenodo is somewhere in the cloud to Texas. So nothing of that obviously happening locally. It's a data set with something like 250,000 rows, so it's a sizable data set in the sense that by biological standards it's not necessarily sizable. So I'm doing actually some analysis for VGP here. I have data sets with 50 million rows, so that kind of gives you the perspective on the scale here. So it needs to upload it. Where columns are, and since we're all doing this, just give it. There is no such thing as real-time genomics. Wait. Any questions in the meantime? Yes.
We didn't get the link.
Which link?
For the data link.
Okay. So the data link is in the tutorial. If you get to this tutorial, then you're going to get that link. That's what you... Anybody else having that problem? Huh?
Yeah.
Oh, okay. All right. Well, good. Tell me. So you go to training.galaxyproject.org. Once you get there, you will see something like this. Okay. Then you click here. And then you scroll a little bit. Just go a bit further, and that's the Data Manipulation Olympics. That's what we have. And so when you click on that, you will see this, and upload data. This is the link. And you don't have to kind of select. If you just go, there's this copy button, so it will push it directly into your clipboard. Okay, so now it's green. Everything is good. Green is good usually. So the difference between Galaxy and if any of you remember Affymetrix arrays, then in Affymetrix arrays, green was good, green was bad, and red was good. Well, here green is good and red is bad. So kind of a more logical scenario. So let's look at this data set. So if you click on it, it extends. It has about 250,000 lines, and it's just a tab delimited data set. You can click on this eye icon, and then it will just be shown here. So it's just some tab delimited data. Believe me, all biological data sets look exactly the same way. It's just sometimes you have chromosome start end, or gene name and expression values, or whatever else. But it's basically all the same. If you go, so what I'm doing, I'm switching back and forth between the Galaxy tab and the tutorial tab. So I'm just going to go back and forth. If you have a big screen, well, nobody of you really have a big screen here, but if you have a 50-inch curved monitor, you're doing this at home, you can put two windows side by side. But on a laptop, it's a little more difficult to do. So hence we have two tabs. Okay, so let's start with data type conversion. This is, it's a story of life for many of us in this business. Is that you get a data set, you feed it to something only to see that the format is wrong. And usually for stupid reasons, like it's tab delimited, but it wants comma separated values, or the biggest problem in biology, we will see that next time, is 0-1 problem. Is that sometimes chromosome numbering starts with 1, and sometimes it starts with 0. And that can create a really Nobel Prize-winning results if you're trying to translate things into proteins. So there's all sorts of interesting things. So let's convert it into comma-separated values. So that just explains a little bit how the Galaxy, what you can do with the history items. So there are 3 buttons here, and what we need is a pencil. And we can just do data set conversion, because for tab delimited data sets we have kind of a pre-canned converters. One of those is from tab to CSV. And so if I do that, what happens is that Galaxy actually takes that data set, runs a job on it. That's the job. It runs a tool. In this case, it's not very sophisticated tool, just replaces tabs with commas, but it creates the new data set. And so this is why this panel is called history. This is your first data set, it's your second data set, and up until we get to 150 millionth data set, they'll all be here. Probably the biggest history that I know of on the public instance have an order of 200,000 data sets. So it's quite robust. So it can deal with the modern data. And it's probably COVID-related data set. So now we just converted data. So we have all this cut out. All right. What else?
How do I know there was no mistake in transforming this data? How do I know there was no mistake?
Mistake, you mean it forgot to convert into commas?
Yes.
Well, it's not a quantum computer, so no. It's not probabilistic game. It's well. Do you trust your calculator when you calculate taxes?
There could be a space missing in the original data.
Oh, then it will
missing afterwards.
Then it will complain. So it's actually a very good. I mean, how do you trust the tool that there are no bugs? Well, you can't really trust any tool. But it's so.
I might say, I
This is
don't
Nate.
know about this specific tool, but many of the tools, we don't, as Galaxy, write most of the tools. We just wrap them into Galaxy. So a tool like this is probably using standard community utilities to convert tabs into spaces. So the bug would generally be there, right? These are.
But we haven't checked the data, but it looks like the way you expect it to look at this point.
Right. You can open it up. You can look. You can see. Okay, it appears to have converted.
Well, I guess.
And you can always write something to validate that if you wanted to.
One check you can do is you just count number of lines. Is your number of lines in your input and output the same or not? Well, here, here it estimates because upon upload it's seen that there are too many lines, so it didn't actually compute. It gives you an average, it gives you an estimate. But here, because it's actually ran through the entire content of the file, it gives you the exact number. It actually will compute the number of lines on that file in like half an hour, so we'll make sure. But it's yes. So as Nate pointed out, we wrap tools. So in this case, I don't know, it's probably using some of the Unix commands. But if you're doing, for example, read mapping, well, you use some of the tools like Bowtie or PWA, so you have to trust them to some extent. It's not really. This is where separation of blame happens. It's not our fault if there is a bug in that tool.
There's a great Unix command for looking at the last X number of lines in a huge file, any file, right? So it's what? It's tail or
Well,
footer?
tail just gives you the last lines of them.
Yes, so you can see if it ran all the way to the end. So that's
Yes.
the way to go.
Yes, you can certainly do that, and there is a tail command here in Galaxy. So
It just runs Unix tail.
yeah, so it's called select last. Well, let's do that. So let's it's good, great point. So here's what I'm doing. So we're deviating from tutorial, which is good. So I just went to text manipulation and I found the select last, or you can just type last in here and it will find it for you. So let's run our first real tool. So you clicked on the tool, it shows you the interface for that tool. This is parameters for that tool, and there is some description of what it does. In our particular case, we want to run this on 2 data sets because we want to compare them. So this is what these buttons do. So you can run it on a single data set, and these are your choices. They're exactly the same what you have in the history. If we would have more data sets in the history, we would have a larger drop down. But you also need to understand that it only shows tools which it only shows data sets from your history which are appropriate for this tool. So if I had for example, a binary file, some zip archive or I don't know, or HTML file or something else, it will not work because Galaxy has notion of data types. Anyway, but so you can run it on every tool. So you can run this twice, first on this and on that, or I can just press this button. You can also, just drag data sets, but in this case I want to run it on 2 data sets. So I'm going to click this thing, multiple pages, and just select 2 of them. And just at this point. All right. And I get 2 outputs because I ran the same tool twice. Are you guys all doing this? Anybody get a yellow one? Is it cooking? It's because of you. I didn't see it. We have interesting thing called kind of a window manager. So if you click on that thing here, you will get a check mark. But what it allows us to do is let's look at this data set. And let's look at that data set. So the last one is Yapkul. So in this case, at least it didn't screw up the number of lines. I mean, I cannot tell you anything about columns, but let's hope. So okay, so we validated that. Any questions? Good. So we can do, you can do various kinds of sorting. I don't know if we actually want to do sorting. Sorting is kind of obvious what it does. So in case of sorting, we'll just use sort tool. And sort tool is interesting because like any sort tool, it can allow sorting in multiple columns. So we can sort on, let's take our original tab delimited data, and let's sort it on, actually, what does tutorial want from us? They want us to, well, let's sort it by year, okay. How do I know which column is a year? Well, it's probably, it's the column, it's column 12. So let's do this in column 12 in descending order. This file, this is sometimes, it's also one of the classical problems in any kind of tab delimited data, is that sometimes your files have headers and sometimes they don't. And sometimes headers are labeled, so it's a header, for example, with a hash sign, and sometimes they don't. So in this case, we don't have that. But we actually don't want to sort that line. We don't want to include that line in any sorting that we do, so we're just going to skip it. So I'm just going to tell it, skip one line. And so we can sort by year. And if you want to play with this, you can then sort on a different column, and so on. So you can sort on multiple columns. Let's sort by year and birth year, for example, column 4. And while this is doing, you can just browse sort of what data manipulation options are available here. Any questions? So while it's doing this, I can show you something. So I would probably name this. And some of the things that you can do with your history is you can share it. So you can share it with somebody explicitly, or you can just make it publicly available and share URL. So for example, you're writing a paper, you're doing analysis here, and you can essentially provide this URL as your supplementary file. And you can export history into a file explicitly, or you can also export citations. So what this automatically will do is it will create a file with citations of all tools that were used in this history. So something that two developers would appreciate. Okay, so it's done sorting. And so it's sorted by Olympics year and by birth year. So when you sort on multiple columns, this is sort of like grouping, right? So you sort on one column, and then all the groups, well, we're actually going to do grouping in 10 or 15 minutes or so. So it would sort, so for example, for everybody who participated in 2020 Olympics, it would also sort them by birth year in this case. I didn't realize that such old people participate in the Olympics. But anyway, maybe it's chess. Okay. Questions? or any suggestions what you might want to do. If you have any questions, you have any real life examples that you want to see how we can do them here. So okay, so filtering is obviously an important thing where you want to filter on a certain value, and this is where we get a little bit into, I guess, a little bit of programming. Well, not really, but because here you need to set an expression, how you're going to filter, on what value. And so let's look at our original data set and see. So how about, I don't know, let's filter by sex. Or actually, let's filter by country. So how many French people do we have there? So and so this is going to be which column is that? Yes, it's column 10. So we need to fix that. We need to header lines here. So this is column 10, and so here's my search term. So column 10 equals to FRA. You have to quote it because it's not a numerical value, it's a string, and we use double equal signs because it's a Python expression, and in programming languages like Python, single equal signs is an assignment. This is when you give a variable a value. In this case, it's a test. You're checking whether the content of column 10 actually has that value. And so again, we want to skip that header file, and I'm still gonna be running this on dataset 1. You can run this on the result of sort, whatever you want to do. But I'm gonna run it on the original file. So some notes here. So you can do much more complicated expressions. So you can obviously, in this case, you're testing equality. You can obviously test larger or smaller, larger or equal to, and so on. And you can even check things like this. So this is, for example, if you split column 2 on a comma. So suppose you have some, in column 2 you have something which is comma separated. And you want to check, do I actually have 4 items in that string separated by comma? So what I'm doing here is that I'm splitting it. It creates a Pythonic array. Then I'm checking the length of this array. If it's smaller than 4, then my filtering criterion is correct. So you can use a lot of Pythonic expressions here, which is, if you have never programmed before, might look scary, but in fact that's where the power comes from, because that allows you to enter arbitrary expressions in there. All right, so that's filtering. Counting. So in this case, I think we're gonna do count occurrences of each record. Let's give it some data set. And this is good. So you see you cannot select anything. But boom, here it works for some reason. And here it doesn't. Because here, as I was mentioning, you can only select data sets from the history, which comply with the tool format requirements. So this tool doesn't know what TSV is. So, because in this case, because it works, for example, with the tabular files, and it will sure work fine with the comma-separated value because it's defined, you know what the fields are. So let's see.
It let me pick, when I picked the first data set, it does let me pick this.
So what's the problem?
No, it will. Like if you switch back to one, yeah, and then in that box you can actually pick, like click inside the box.
Oh, I see. Because it is, okay.
Can you say where you found count?
Yeah.
I'm having trouble finding count.
Okay, go here. Type count. Yeah, and it's going to be here. Or if you type count occurrences, then it will find it for you. I just, if you read my email, you probably know that I cannot type. So therefore, long words don't work for me. All right, so sorry, it actually. Okay, so the days where I actually knew everything how this works are past. So it's way too complex. So so actually it allows you to select data set. It's not sure which columns to choose, and you can. Let's do this by which column by. It wants me to select. So tutorial wants us to use what? Formula. And what else does it want us to do? Okay. Let's see what happens. So we're getting into various grouping operations. Some of you might be thinking, well, can I just do it in Excel? Or if I know R, I'll just create a data frame and do this in R, God forbid. Or if you actually like normal programming languages, then you do this in Python and Jupyter Notebook and so forth. You can do this, but the power, just imagine that you need to do this on, I don't know, 1,000 data sets. So this is where the power comes from the ability to organize data sets. We have not seen this today. This is what data set collections are. This is what I'm going to talk about next Monday. But also the power of compute, which is on the back of that system. And so here's what we got. So we were counting by column 11. So what this does is that it picks all the unique values from that column and counts the number of occurrences. So I don't know if that could be, if you want to translate it into biological terms, you have coordinates of ChIP-seq peaks, and you want to certify them by chromosomes. You would just do this on the chromosome name column. Or you want to do this by genes, or however you want to do it. It's all the same tab delimited data.
Let me ask you something. You have just mentioned about R and Python. How far is this from Pandas?
Well, Pandas is a data frame, so it's obviously you can do all of this in Pandas as well. But and go ahead. The challenge here is again in fact, this is not a bad data set to show this for because this is data set with 250,000 lines. But yes, you can do this in Pandas. So in this case, you would have to do what? You would have to install Jupyter, make sure you have server client. Of course, you can use Colab if you want to do that. Yes, you can do that. Now again, add additional dimension here of doing this on multiple samples. You can script that too, obviously. So, but just imagine that you actually have a stack of directories with multiple with the files like that, and you have 1,000 of them. And you need to do filtering, counting, grouping, and then combining them in some form. You can do this all in Pandas. There is no question there. But in order to do this in Pandas, you would have to write first, a loop to go through these directories and so on and so forth. But here you can organize data, and then basically in one click run this on all 10, 100,000 data sets. That's so. And another thing is that you usually use Pandas. So for those of you who don't know, Pandas it's a Pythonic. It's an open source library for Python, which kind of works with spreadsheets. Well, with data frames, they're much better than spreadsheets because you can have very large data frames. And then so it allows you to do various things that we're doing here. But normally Pandas is on the end of your analysis, because in biology or in I don't know, in high energy physics, in computational chemistry, well, I obviously know more about biology, so you get some gigantic number of reads, then you do something with them, and then at some point in the end, for example, if you're surveying population for a certain variant. So once you do all of this, once you map, once you call the variance, once you filter the variance, once you assign some quality values to the variance, only at that point you get that table, which you can then manipulate. But you have all this funnel where you start with really large data sets, and you get it down to a manageable table like this, and then you can use Pandas. And in fact, kind of the global philosophy of Galaxy is that it's good for doing this really large manipulation, and then you can, because, well, here we're filtering, grouping, but sometimes you actually don't know what you want to do with your data. You get a table, and you want to let me plot it this way, or what's the distribution, or if I exclude these values, what happens? So in this case, you have no choice. You have to use something like R or Python, but you can actually start, and this is in a few weeks, you can start Jupyter directly from Galaxy, or you can start, I'm not going to do this right now, but you can, there's a series of things. So what happens here is that you actually start you start an instance of Jupyter, which is your personal instance, and because it originates from Galaxy, it knows how to get data sets from here. So it's a Jupyter instance, just like any Jupyter Lab, or RStudio instance, just like any RStudio instance, and but you have access to these data sets. So it kind of provides you a free Jupyter server in this case.
How does OpenRefine compare to Pandas?
How do
OpenRefine?
I don't know what OpenRefine is. I need to try it, maybe. So there's also data frame, something.
Yeah, it's like
And for what, is this Pythonic or?
I'm not sure, but it's similar to what you described for Pandas.
Okay, well, Pandas is not the only thing, clearly. But it's the most popular because it's popular on Wall Street, so it has a lot of support. But fortunately, it's an open source project. But it's really good for working with financial instruments. Let's put it this way. So, okay, counting, grouping. That's an interesting one. So we're getting into a little bit more interesting analysis. So in this case, how tall was the tallest athlete for each sport? So you can already see that it's a kind of it's a loaded question, because first you need to compute, first you need to know what sports are unique to this data set. You need to organize your data by sport, and then within each group, that's why it's called grouping, you will look just at this group and find what's the tallest athlete. If we're dealing with genes, so it's the same thing in a particular condition. What's the gene which is expressed the highest, or what's the gene which is expressed the lowest? It's the same thing. In this case, just instead of grouping on sport, you're going to be grouping by condition. Or you can group by gene and then see sort of at what condition it's expressed to the max or expressed to the min, and so on and so forth. So there are multiple ways of doing grouping in Galaxy. So one of them is it's just a group function, but there is a much more powerful thing called data mash. And all of these tools you can run obviously on a command line as well. So data mash, in fact, I think it's part of the standard Debian distribution now. It's written by a friend of ours about, I don't know, 10, 15 years ago. So it's a very fast tool set for dealing with tabular data sets. It's written in C, so it's faster than Pandas. It's just instantaneous. And it has, the main function here is data mash, which we're going to use now, but it also has this reverse and transpose functions where you, for example, if you're dealing with image data with pixel values, then you can transpose them if you're dealing with any matrices. But let's do that. So this is already a tool with a little bit more complicated interface. So so this tutorial, by the way, is written by Saskia and Helena. So the Galaxy Training, it's a community effort. It's something that we used to do, but now there are more than 100 people who contribute these trainings, and they're actually kind of responsible for maintaining that framework now. They're based in Rotterdam. Actually, Helena is from Texas A&M previously, but now she's at the Erasmus Medical Center. So why I'm saying this is that their tutorials are usually really good. So since you can group tutorials by who made them, if you see Saskia or Helena in tutorials, that's a seal of approval. All right, so it tells us that I group by field 15. This is where the height is, this is where the sport is. Then we do need to sort. It has the blah blah blah, and on each group we need to perform maximum on column 7. Let's unpack this a little bit. So. So column 15 is sport, and column 7 is height. So let's group by 15. We do want to sort the input because, one of the reasons data mash is fast, it assumes things are sorted, but in this case, it's not. I don't know. Maybe it's sorted, but the way to ensure is just to say yes here. It does have a header line, and then we need to do maximum on column. So I need to do this on my original conversion to CSV, so data set number 2. So column 15 here, and here we're going to have maximum on column 7. And you can add more. So you can group on, for example, it's probably unfair to group them by height without grouping them by sex, for example, because, well, on average, males will be taller, but let's just mesh them together in one group at this point. So what this tool will do, it will look at column 15, find all the unique values, then for each set of unique values, compute the maximum height. I think this will be already after Thanksgiving, but another functionality I'm not talking about right now is workflows. Because once you've done an analysis like this for the first time and you think it's good, so you know, okay, here you need to do this, this, and that, and that. All right. That's an error. That's a red one. That's bad. Okay. All right. So how is that possible? It's in so that's a validation error.
Column 6 there, one index is the birthplace. So I'm guessing data mesh is using the 0 index.
Data manager for what?
No, data mesh. So you said column 7.
Yeah.
Which is height, and you're using the 0 index.
Well, but you cannot use different indices in one search, right? So, okay, so this is an error. There's the bug. So when you get that something like this and you're sure it's not your data, then you can click that. And you can report that. So we will get that and we'll see what's going on. So, and also to rerun this tool, because you know we filled some values, we don't want to fill them again. There's always this rerun button. So let's see. So you're saying that this is indexed by from 0, then this is okay.
Right, you pick maximum for 7.
Then that should be indexed by 0 too, then, right?
What is
Yeah. Let me try again. Maybe it's.
Did you pick the tab option?
Oh, I see. I see. So you think it's better to do it? Well, it shouldn't matter. But let's see. So what I changed, instead of the comma separated values, let's choose data set. Let's choose the first data set, the original data set that we uploaded. Failed as well? Interesting. It's a legitimate error, because if you're trying to find a maximum, then it's expected you're gonna get numeric column. Well, it's doing something.
Mine worked.
I think this will work too. So there's something about comma delimited values, which it doesn't like, and I actually don't know whether it's the tool problem or it's our problem. What we can do, I mean, 2 hours sitting in one place, okay, is a long. So let's do a 5-minute break and then go get more. Huh? So, and so the output of this is, well, let's buy support. And see, there's an infinitely high person for automobile racing. So it's the same thing for alpinism. That usually indicates that there's a problem with your data there somewhere. Okay, so right now it's 3:04. Let's get together at 3:10. And I'm here, so if you want to ask questions personally, I'm not going to get to because I already had enough.
Will there be more outlets next time?
Hmm?
Will there be more outlets or like extension ports or something?
We can do that, certainly. Good point.
Computer class and no outlets.
No problem, yes. It's not a computer class, it's a pretty bad room. Good point.
Yeah, sorry to take the one.
No, that's fine.
So, I didn't realize that this was 2 hours. The budget is 1 hour late. So I'm going to have to
Yes.
So I could do that.
You can pick anything else, but yes, that's what
But if I go through that, that'd be awesome.
you'll be all. I'll email you.
Oh, I wrote it down. I wrote it down.
Okay.
That value.
more interesting.
So at least for me, I think it's saying that there was like a NA for some of the ages. Because it's
But it's still, in this case, it just should skip the line, so I'm not quite sure why it does that, right? Okay. But I need to make sure, because I don't understand what's going on. So it's C15 minus 4. C12 minus 4. Bet money in this. So I'm doing something stupid, but I don't know what it is. So, I'll figure this, I'll tell you, I need to spend some time on it and see what I'm doing. So I will come back to that particular example next time. But let's just still, but we still need to compute the age. So let's see. We used to have a different tool here. Maybe not. I don't know. Let's but I will come back to this because I need to understand what's happening here. So let's do find and replace. Let's find the right tool. Actually, so I forgot to tell you. So one thing, the problem you may be experiencing right now is that you go to tutorial, you can't quite find the tool. So there is a way to deal with this. If you click on that icon here, then you would actually get the training materials from inside that window. And if we go here, and go to the same place in the then these buttons will be live. So what this means is that if you click on that button, it would actually load the tool right away. So you don't have to search for it. And again, in order to do this, you just click here. It remembers where you are, so it would bring this model into the browser frame. So you can then click away, but it doesn't disappear. It remembers where you are. So if you click on the hat again, you will get it. So this is the tool I actually was looking for. It's called add expression. Let's compute the length, because I need to compute the length. I need to compute the age. So I and what are we doing? We are doing C12 minus C4. This tool, which I'm just running, it's one of the oldest Galaxy tools. It dates back to like 2004. So what do we have? There's something wrong with this input file. I don't know what that is. So it just doesn't like it at all. So it's probably
Mine worked.
well, that's because your stupid teacher selected the wrong thing to do this on. So okay, so this data set, that's the expression. Doing live demos is very dangerous. But see, this is old tool, so it's not behaving really well because it failed really. Didn't compute anything. So this is. I don't think we have many tools which do it like so. It's called silent failure, and that's the worst kind of failure you can get. It's a very old tool. So the new tool, which I couldn't get to work, that's the one to use. But I need to figure out why I couldn't. Okay. So what do we have here? Okay, well, finally. So that's the age at the Olympics. Okay, so what do we want to do here? So actually, I'll go back and I will open tutorial in here, so it's easier to deal with. Okay. So, that's a good example. So in this file, Athens, they are spelled differently. And RNA-seq, gene expression analysis. The gene names, that's a hell in itself. Because, some people call it INC4A, some people call it CDKN2A. So that's kind of the same thing here. So almost like Athena and Athens. So we are going to use kind of a regular expression for this, although it's not really sophisticated in this case. So let's see. So the column is going to be column 14. Because that's where the C is. And we just, at this point, we're not gonna use any syntax of regular expressions, really. So in this case, it doesn't matter whether we have header line or not, because header line doesn't have Athena or Athens. It will just be skipped. So this is just a simple find replace. But using regular expressions, so regular expressions is a way to create patterns that can be matched. And here there's a little primer on regular expressions. It's a very powerful tool for parsing or matching things. For example, could be a situation in which, again, your gene names contain something in them which you want to convert to uppercase or to lowercase, or you want to, or your gene name contains several parts separated by a dot, for example, and you want to get rid of one of those parts. There's an endless amount of situations in which you can do this matching, and so you create a pattern. In our particular example here, we're just looking for Athens. There is nothing, we don't really need to specify the pattern because the pattern is well defined. It's an exact word. But you can be in a situation where you want to find a word which has a letter A, and that letter A is the first letter. Or you want to find a word where there's a letter Z, but it's the, or letter A, but it's the, again, a last letter. Or you want to find words which contain A, B, X as a third letter. So you can, using this syntax, which can get quite complicated if you're writing a very long expressions, but you can encode anything. It's very powerful, although it's a bit, it requires you to get used to, but all the programming languages, certainly Perl, Python, Unix shell, they all support this. And so the syntax is like this. So, for example, this is a group of characters. So using expression like this, you encode a single position which has letters A, B, or C. So either one of them will work. So it's a single position in the word which has these letters that will be matched. Same thing, but it requires now that they need to be at the beginning of the word. And so this is, any digit in word, in white space, it's syntax which can get. The problem with this is that dot is any character, but sometimes you want to match a dot. So in this case, you escape it. You use this slash as an escape character. We're going to use that in either next week or on our third lesson in more detail. So this is how they encode beginning of line, end of line, and so on. And then they can get for example, so give me all chromosomes which have one in a where the first digit after current, which is often used to define chromosomes in files. So that would return 10, 1, 11, 14. We'll return them all. Or this is, for example, another example where you're matching the two. So you are encoding them in this kind of a weird way. But again, in this case, we are just doing that. And so in this data set, in all the instances where it had Athena, it replaced them with Athens. Obviously, it ignored everything else. It also ignored entries in that table which have no CD specified. This is why we're getting actually a smaller number of rows compared with the original data. There are, well, since we only have 10 minutes left, you can obviously remove columns. There's a way to do that. But one thing I want to show you before we go is you can find unique values. So, for example, it's very similar to count that we did when we were counting. What we were counting? We were counting sports, or what did we do? We were counting the different Olympics, how many entries we had for a given Olympic type. But it's basically what this tool did. It found all the unique values and counted how many times they occur. So unique tool is a tool that does the same thing. It will find unique values in a certain column of a given file. But the last thing I want to show is how to join files, because often you want to join things. So in biological problems, you will have two kinds of these operations, two kinds of joins. One join is on a single value. This happens when you, for example, you want to join, you have one table where you have social securities and addresses. You have another table where you have social securities and I don't know how many times they were abroad, and you want to join them. You join them on social security. It's going to be your column. So if you have two files, and if the entries share the same social security number, you join them together. This is that kind of join. However, in biology, because we often deal with intervals, so we have a gene which on chromosome 1 allocated between position 10 and 100. And we have, for example, a variant, or we have, I don't know, a ChIP-seq peak with coordinates, say 20 and 25. So we can join these two, and they will be joined if that ChIP-seq peak is inside that gene. It's called genomic arithmetics, and this is a different kind of join. It's a kind of join which we're not doing right now. Right now, it's going to be joining on a single column. I'm going to talk about interval logic. So this is where you deal with intervals. Intervals are obviously the things which are defined by start and end, because ultimately all genomic data is this single-dimensional, well, I guess it's two-dimensional chromosome and start and end positions. And for that, there is a completely different set of tools, and actually, just before I go this to probably confuse you even better, there's a whole set of tools called BAD tools. And you know, to somebody who doesn't know biology, BAD, it's about hospitals or something like that, but in fact BAD is a browser extensible format. That's just a format. So this is a group of tools for comparing data sets which are defined as intervals. So SNPs versus genes, you know, promoters versus ChIP-seq peaks, things like that. This is not what I'm doing right now. I'm just giving you a preview so you know that there are two kinds of join. You can join on the unique value, or you can join whether things overlap or not. So, and here we need a second file, obviously. So there's another file which we want to upload. So we just do exactly the same thing. Click copy, go back, click on upload, select paste fetch, stick it in here, and just upload. Yes.
In the case of RNA-seq, there must be databases that where different gene names used for the same gene are.
You would think. You would think, yes, but that's no. Well, maybe, but
there must be some kind of tool where you can homogenize the data. No?
Well, Do you know such a tool?
No, I wonder. I mean, I don't
There's
know. But
probably. I think that it's often, the large resources like UCSC, Center for Genome Browser, or AMBL things. They try to do that, but in general, there is no a good resource which would provide you with up-to-date mapping.
there's no universal yet.
No.
Or for instance, to compare gene expression data between mouse and human, they often use different names.
It's, or Drosophila, God forbid,
Yeah.
because this is completely different, or C. elegans is completely different. And, like in Drosophila world, they don't even use plus and minus for strands. They use Watson and Crick. So it's W versus C. So yes, this is the tragedy of our, or it's good for me. But in general, it is the, what did I just do? Sorry, I think I'm just getting really stupid here. So I don't know what, I think I'm, okay, let's close this. Let's reset this. Okay, so instead of the file, I uploaded its URL. There's also a problem even in the single species like human, for example. I don't know if you read, but it was in Nature already a good half a year ago. There is a T2T version of the human genome. T2T means telomere to telomere. So they generated a sequence which is now complete. It almost has no gaps. It's thanks to the long reads. But it's not really used that much. And the problem is that for all the medical, clinical, and basic research things, the previous version, HD38, it's much better annotated. You know where genes are. This information hasn't been transferred to T2T yet. And so it's actually, everybody like, why am I using this if it doesn't have my genes?
No interesting information in addition of the sequence anyway. It's all repetitive.
Yeah.
Repetition, correct?
But the problem is that these repeats change coordinate system, right?
Yes.
So if your gene before was in chromosome 12 at 52 million something, it's no longer there because you filled all the gaps. So now you need to, and there is a procedure. It's called liftover, when you take annotation of one genome version and move it to another genome. But this is done. It's kind of indirect. It's done via alignment. So they align genome versions to each other, and then that gives them an ability to translate coordinates. And it works in most of the cases, but obviously, and if you're lucky to study something like sex chromosomes, where you have palindromes, so it's like a Murphy's Law, is that your gene will never be there. It's the, okay, so, all right, so I loaded this thing, and it's just an information about countries now. 3-letter codes, 2-letter contents, and things like that. And what am I trying to do here? Okay, so the question is, how many? So this is for exercises. You can do this later. But what are we joining on? So we are joining on countries, so we can get. Well, let's look at these data sets again, so we actually understand what we're doing. Okay, so this. So this is just crazy information about countries, various codes, and so on. So, yes, Aruba is part of NL. Yes, we know that. This is actually also, it's not genomics, but it's very similar. If you're doing any geospatial types of analyses, you're going to go crazy by converting 2-letter country codes into 3-letter country codes, and vice versa. It's all the same, people, all the same. In high energy physics, same idea. Instrument IDs, and it's But basically, the point of this exercise is that in the table with athletes, I have countries. And I don't know, maybe I want to call them. So in order to do that, I need to know there's actually a phone codes here as well. So I want to have one table where I have all the information about athletes plus all the information about their country. So I'm just going to join them on the country name, I suppose. So I'm joining on this NOS, it's probably country code. So yes, NOS column, that's the, and so let's just do that. So, and we'll be done, I promise. So, what am I doing? So we're joining Olympics on column 10 with country information in column. What else do we need? Headers, yes. When we were designing this thing, we were wondering if you click that button, wouldn't it be nice if it actually pre-fills all the values? But then we decided against this because then it will become like driving with Google Maps. Because when you drive with Google Maps, you have no idea where you are. And so you just trust the Google Maps. And so the same thing happens here. If we refill everything, then nobody will ever look at the two interfaces. So this is by design in a sense. So again, the join we're doing right now, it's a relational join. In relational databases, you would do this join on an index, on a particular key column. In this case, this key column is this country code.
I have a question.
Yes.
So you can of course do all this also in R, right? Like
Yes.
Starting out, but is this like when would you use this Galaxy tools instead? Would it be for like extremely large databases?
No, I mean it's a convenience. All these tools are not mainstream analysis tools. Mainstream analysis tools would be DSeq or Bowtie or these are just convenience tools. I mean you don't know. It's possible that imagine that you have coordinates in the normal format where you have chromosome ID and then you want to feed this data to a tool which doesn't like the chromosomes start with CHR. To get rid of CHR. It's a convenience tool. And today, the reason I'm showing you this is not because I want you to do relational joins or grouping or filtering only in Galaxy. It's just it's a general introduction to how Galaxy works. Imagine you can take any other tool or do anything. It's just sort of to introduce you to the interface so you know how things get added here. So that sometimes they're red. And how you set the parameters and so on. So it's we're not doing any analysis per se. We're going to start on next Monday. So today, just a taste of this. So, and this is how the joint data set look like. It's a very large table now because we essentially, if two rows match, we concatenate them together. So it's going to be. Well, we don't duplicate the value of the column on which we match, so in this case it probably B. So it becomes very, very wide this way. So I will probably stop here because I frankly don't have voice anymore. Just look through this, and if you have questions, then ask me next Monday or email me. Although you should know that I'm horrible with emails in general, so you should usually email me twice to get any answer from me. So, okay, and tell more people to come. So I at least, but thank you for coming. And as I said, I'll have better food next Monday. I'll actually have. And do anybody has? I'll ask for vegan options and so on. So I'll send another email. Sure.
For joining.
Yes.
This will look only the, like, so there has to be the same column name in both the.
No.
No, it doesn't have to be like that.
You can, no, names don't, pretend that columns don't have names.
Okay.
They should have values which it makes sense to join on. I mean, you can join, we can join, you can try on other columns, you're just going to get nothing in return.
I think so. Got it. Yeah.
They don't match. It's, you only join on things that you expect that have the same, you expect on the column which represents the same thing in two different data sets. Any other questions? I'm here, so.
Thank you.
There's like another, are you familiar with other like online browser-based tools like Galaxy also available in the US?
There are, well, I mean, there are other, for example, workflow engines, but there is no, well, there are commercial platforms. There's, for example, DNA Nexus, which doesn't have that many tools. So there are commercial platforms, but they, for example, they don't have obviously free compute. They don't have similar amount of tools, and they don't have the same smart logic for dealing with many data sets. So there is really no direct comparison.
Okay, this is like the best one.
I'm not saying it's the best one. I'm saying it's the one that exists. And we've been doing this for 15 years, and so we're still on the horse in a sense. So.
Okay. Thank you.
All right. Thanks for coming. All right. Okay.